This video is on the notion of an ordered pair of sets. Recall that in the axiom of pairing, we stated that if we are given two sets, A and B, and they could be equal to each other, we can put them together in a single set, which let's call it C, which is denoted like this. Now, in this object, in this set, the elements A and B do not appear in a certain order, even though in the notation there is a certain order, but in fact this set is indistinguishable from this one. We can back this up with the axiom of equality of sets and say, look, both of these sets have the same elements, therefore they must be the same set. So when we pair two sets into a set, the order does not matter. But a lot of the times, and in fact almost in every corner of mathematics, order does matter. When we write words in English, order matters. If I rearrange words, letters in a word, I might get a different word, or I might not get a word at all. And so it is useful to have a notion of an ordered pair, a pair where order does matter. The notation for an ordered pair is as follows. So we use round brackets instead of the curly brackets, and it is defined in a certain way. Now you see, without any further discussion, if I just write an expression like this, I cannot say that this is an object in the universe, because all the objects in the universe are sets. And so I have to indicate what the elements of this thing are. If it doesn't have any elements, then it's going to be the empty set. And then this notion will not be very useful, because for various different kinds of A's and B's, the ordered pair will always be the same empty set. Now, we have to, and we want to encode, we have to, from the purpose of the notion of an ordered pair, to encode this as a set in such a way that the order will matter. Because when we put things in a set, the order does not matter. So it feels a bit contradictory. How we'll be able to define an ordered pair with the order mattering? And definitely not this way, because here the order does not matter. So a way that this can be done, which is due to a mathematician called Kuratowski, at least that's the best we know, that he is the one who came up with this notation. This construction is the following. So we're going to have a set, and this set is going to have two elements. One of it will be that thing, and that encodes the contents of the ordered pair. So to give the order, since there are only two objects in here, it is sufficient to say which one comes first or which one comes second. But let's agree that we're going to point out which one comes first. Since there are two things, saying which one comes first is sufficient to say what the order is. So we're going to do that by including another element in this set, and that other element will be a set consisting of whatever comes first. So that will be a set consisting of A. So this is the definition of an ordered pair that we take. It's a set having these two elements. In a picture, we can draw it like this. So let's say we've got A and B. And what we do, as you see, we put them in a set. And that's one set, right? And then we put A alone in a set, and that's another set. And now we take the set of these two things, and we can do that by the axiom of pairing. We can put any two sets into a set of those two things. And that final set is what is called ordered pair AB. Now, how do we know for sure that the order has been retained? In other words, how do we know that AB will not equal to BA? Or perhaps unless A is equal to B. Or how do we know that the ordered pair with this definition is actually uh, from this definition, it's actually possible to recover the contents. Um, in other words, two different contents cannot give the same object. So how do we know that if AB equals CD, that it must imply that A equals C and B equals D? These are all the things we want from an ordered pair. We want that to be true in order for the ordered pair to function its purpose, right? And so all these things, and in fact, the first one of these things we mentioned here will be a consequence of the second one. If you put C equals B and D equals A, their equality will force A and B to be equal, which is logically the same statement as this one. So that can be established by mathematical proof, and there is a separate theorem claiming this, and you can try and try to prove the theorem. And if you can't prove the theorem on your own, maybe you can try discussing with others or look up the proof and see how it works. It shouldn't be difficult though, just by applying the definitions and the axioms to establish this as a theorem.